Hello and welcome to this film about calculating different types of chemical formula. It's another one of the quantitative chemistry films, and hopefully by the end of it you'll know the difference between an empirical and a molecular formula. You'll know how to calculate an empirical formula if you're given the masses of elements that react together to make a particular substance, or indeed if you were to know the percentage of each element in a substance by mass. And then last of all, we're going to look at how we convert an empirical formula into a molecular formula if we're given a little bit of extra information. So let's start off, importantly, by understanding the difference between these two types of formula. Now, a molecular formula, which can only really apply to a covalent substance, because only covalent substances have molecules, but you could have the formula of an ionic substance too. Molecular formula tells us about the exact number of atoms in one molecule. Okay, so for example, if I choose carbon dioxide to illustrate this, the exact number of carbons and oxygen atoms in one molecule of carbon dioxide is 1 carbon and 2 oxygens. Okay, and the molecular formula will always be a whole number multiple of the empirical formula, and we can understand that better if we understand what an empirical formula is. Because, and this is a really important definition to know, it's the simplest whole number ratio of atoms in a substance. Okay? Now, here the ratio of atoms is 1 carbon to every 2 oxygens. Okay? Now, I can't make that into a simpler whole number ratio, i.e. to use smaller numbers to describe the same ratio. Okay? So, in actual fact, the empirical formula of carbon dioxide is the same as its molecular formula. That isn't to say that this isn't a whole number ratio, multiple of that. It's just 1 times that, so they're the same. But if I was to choose a substance like glucose, which has a molecular formula of C6H12O6, so 6 carbons to every 12 hydrogens to every 6 oxygens, well, I can write that ratio of 6 to 12 to 6 as a simpler whole number ratio of 1 to 2 to 1. So the empirical formula of glucose is CH2O. This doesn't tell us about how many atoms there are in one molecule of glucose, it just tells us about the ratio of atoms in a sample of glucose. Okay, so to find the molecular formula, if I'd found this, I'd need some extra information about how big the molecules are. But often if I'm doing an experiment where I'm combining elements together to form a new substance, I don't know how many molecules I've formed, so the best I can do is to get a ratio of the reacting atoms. Now, bearing in mind what we're trying to do here, right, so in other words, we are trying to find a ratio of atoms, and remember, we're going to try and put them in this ratio into a formula. So here I've got 0.243 grams of magnesium reacting with 0.710 grams of chlorine. So my formula is going to have magnesium and chlorine in. I don't know what numbers to put into it yet because I don't know the ratio of atoms in it. Okay, but if I'm going to count atoms and I'm going to find a ratio, then I'm going to need to know the number of moles, right? Little n, I want to find the number of moles. And remember that the formula for the number of moles we've learned up until now is the mass divided by the molar mass. Okay, so in other words, if I'm told the mass, I'll be able to find n. Okay, and what I'm going to do is I'm going to arrange these things in a table, and the reason I'm going to do this is because when I come to putting these numbers that I find into my formula, it's much harder to make a mistake if I know that this number applied to magnesium and this one to chlorine. Okay, it also gives me a nice easy way of showing my working. Okay, now the masses, I've been told 0.243 grams of that and 0.710 grams of chlorine. Okay, now if I take those masses and divide them by the molar masses, so I'm going to divide this magnesium mass by the molar mass of magnesium, which is 24.3. Okay, and hopefully you don't need a calculator to tell you that's 0.01. If I divide 0.710 by the molar mass of chlorine, remember this is the molar mass of chlorine atoms, not chlorine molecules, so 35.45. Okay, and that would be 0.02, precisely 0.02, but to the same number of significant figures as that one, it's 0.02. So the whole number ratio is 1 to 2. And so the formula of this chloride is magnesium 1, but we don't write ones, and chlorine 2. Okay, so that's the formula of this chloride that we were asked to find in the question. This tells us that for every 1 magnesium there are 2 chlorine atoms. But if this was a molecule, I wouldn't know how many magnesium atoms there were in one particular molecule and how many chlorine atoms, but I'd know that it would have to be a multiple of this ratio. Now if we look at another example, here we're being given percentages of elements and we're being asked to find an empirical formula. Here we're told that we've got an oxide of carbon. So in other words, my substance is going to have carbon and oxygen in it. What am I told? I'm told that there's 27.3% carbon. Now I know that I want to find a ratio if I'm going to find an empirical formula. And to find a ratio, I need to know the number of moles. And the only formula I know for number of moles so far to do with reacting masses or percentages by mass is mass divided by the molar mass. Okay? Now I don't know the mass here. This mass could be anything. All I know is that 27.3% of this oxide is carbon. So is that going to be a problem? Well, not really, because if I imagined that I had 100 grams of it, then the mass simply becomes the percentage, or the percentage becomes the mass, depending on which way you look at it. Okay? So again, I'm going to organise this in a table so that I can't end up with the wrong numbers next to the wrong element later. Carbon here, oxygen there. The percentage of carbon is 27.3%. We've got to do a little bit of work to figure out what the percentage of oxygen is, so that's going to be 72.7%. Now, as I say, we are basically pretending we've got 100 grams of it, so if we can treat these as masses in grams. So I've just got exactly the same kind of problems I had before. I've got to take the 27.3 and divide it by the molar mass of carbon, which is 12.01, and I've got to take the mass of oxygen, in this case the percentage, but I'm treating it as a mass, and divide it by 16 because that's the molar mass of oxygen. And if I do that, I find that I've got, let's see, 2.273 moles of carbon and 4.544 moles of oxygen. And if you can't do this ratio in your head, if you can't see that this number is about twice as big as that one, then you can just divide all the numbers by the smallest of them. So I'd divide this one by 2.273 and I'd find that would be 1. Divide this by 2.273 and I'd find that would be 2. And so this is actually carbon dioxide that we're talking about. Okay, so that's the 2 different types of problem that you often face where you're being asked to find the empirical formula of something. Now we're going to find an empirical formula and then turn it into a molecular formula. And remember, the molecular formula is always a whole number multiple of our empirical formula. So, glucose, whose formula, unfortunately, we've already told you in this film, but it doesn't matter, it's going to spoil the surprise, but not a lot else. We can still see how the problem works. Contains carbon, hydrogen, and oxygen. So, my formula is going to have those 3 elements. It has a formula mass of 180. This means that one molecule of glucose weighs 180 grams per mole. So the sum of the atomic masses in glucose is 180. We'll use that in a minute. We'll find the empirical formula first. So we need a ratio, we need the number of moles. We're given the percentages, but remember we can just treat those as masses. Okay, so organising my information in a table as usual with carbon, hydrogen and oxygen. I've got 40% of that, 6.71% of that, and 53.3% of oxygen. So if I divide these by the molar masses, remembering that carbon is 12.01, hydrogen is 1.01, oxygen is 16, divide these 3 numbers by those 3 numbers, and for some reason this is a step that people who get these problems wrong often omit. They just find the ratio of the percentages and hope that's going to work, but because these atoms have different masses, that doesn't work. So anyway, plugging those numbers into my calculator, I get 3.33 there, 6.64 there, and 3.33 here. And again, if you can see that in your head, what the ratio will be, that's 1 to 2 to 1, then great. If not, then use your calculator and divide all these numbers by the smallest of the numbers, which is 3.33 in this case. So as we said before, the empirical formula of glucose is CH2O. Now, back to this formula mass of 180. My formula mass tells me the sum of all the atoms' atomic masses in one molecule of glucose. I can find the sum of all the atomic masses here. That would be 12.01. Let's just call it 12 plus 2 plus 16. That should say, it's not very clear. Okay, so if I add those up, 12 plus 2 is 14 plus 16 is 30. So the molar mass of the empirical formula, which kind of doesn't make sense because you can't, this isn't a substance, so I can't find the molar mass of it. But if I was to talk about how much 1 mole of this substance would weigh, then that would be 30. Okay, and I can see that the formula mass is 180. So if I take the 180, so the mass of my molecule, okay, and then divide it by the molar mass of the empirical formula. This is what I'm always going to do. I'm going to get my actual molar mass and divide it by my imaginary molar mass. I find that this is actually 6 times bigger than that, and so my molecular formula must be 6 times bigger than that, C6H12O6. Okay, so that's how we use a bit of extra information to turn one formula into another. Now, really and truly, everything we've covered there involves some quite simple maths, okay, but it does rest on knowing how to use some of the formulas that we've covered in previous films, and it also rests on an understanding of what these different types of formula actually mean. If you've got any questions from this film, please feel free to come and ask some questions. The best way to get good at these things is to practice them. Don't think that you're just going to remember it all just by watching this film. If you do get stuck, come and see me or post a comment on YouTube if you'd like to ask a question that way.